Welcome to lecture 6.2 for college algebra. We're going to now look at systems of equations in three variables. So every time we add a variable, the complexity increases. And this is a very challenging lecture, so take your time through it, practice lots of problems, and work with the properties that you're going to learn today. So what we're going to do is to learn how to solve systems of linear equations in three variables. And then we're going to use systems of three equations to solve applied problems. And we're not going to model a quadratic function. We can do that later. A linear equation is an equation equivalent to the one of the form ax plus by plus cz equals d, where a, b, c, and d are all real numbers or constants, and a, b, and c are not equal to 0. A solution of a system of three equations in three variables is an ordered triple that makes all three equations true. An example, the triple 4, 0, -3 is a solution of this system of equations. We can verify this by substituting 4 in for x, 0 for y, and -3 for z in each equation and see that they all are indeed true. The equations are x minus 2y plus 4z equals -8, 2x plus 2y minus z equals 11, and x plus y minus 2z equals 10. Gaussian elimination is an algebraic method used to solve systems in three variables. The original system is transformed to equivalent one of the form ax plus by plus cz equals d, ey plus fz equals g, and h times hz equals k. Now all the capital letters here just represent numbers. So you might say for the first row it might be 3x plus 2y minus 1z equals 14. Okay, so these are all just, the capital letters are all just constants. If you'll notice here at the end we have hz equals k, which could be something like 2 times z equals 8. Well, this is an easy equation to solve. And so if we can get the system of equations into this, and notice what it is, it's a stepping down of variables. In the first one, we have all three variables, x, y, z. In the second one, we just have y and z. And in the last one, we just have the variable z. If we get them into this form, we can work from the bottom up and solve. For example, we can figure out what z equals by dividing k by h. Once we have that number, we plug that value into the second equation, and then we can solve for y. Once we know what y and z are equal to, we can plug those into the first equation and then solve the last equation, actually the first equation for x. So thus the third equation is first solved for z, and then we do use back substitution first to find y and then x in this example. So there are some operations or some rules that you can use to kind of make this, to transform your original equations into this Gaussian method. You are allowed to move any equations you want. So for example, maybe the first equation just says 4z equals 16. Well, you can move that to the end, and that can become your equation 3. You can multiply both sides of one of the equations by a non-zero constant. Well, that's just how we've been manipulating algebraic equations anyway, knowing that if we multiply one side by something, we have to do it on the other. And we can add a non-zero multiple of one equation to the other. We saw this in elimination where we added two equations together, and sometimes we had to first multiply them by something so that we could eliminate one of the variables. And that's all this third one is saying, so that you can add two equations together and you can add multiples of one of those equations. And we did the multiples when we didn't have opposite coefficients and needed to create them. So let's look at how this goes. And it's pretty complicated, or it's a bit complicated. Solve the system x plus 3y plus 2z equals 9 is equation 1. Equation 2 is x minus y plus 3z equals 16. And then the third equation is 3x minus 4y plus 2z equals 28. So the first thing we want to do is to choose a pair of equations and so that we can eliminate one of the variables in them, okay? So what we're going to do here is we're going to eliminate x from equations number 2 and number 3, okay? So equation number 1 is going to stay the same, but we're going to eliminate x using 1 and 2, and then we're going to eliminate x from 3 by using 1 and 3, okay? So it's just the elimination. Notice between 1 and 2, we need to multiply one of these equations by -1 because there's just a 1 in front of both of the x's right now, but we need it to be opposite. So if we multiply the first equation by -1 and then add it to equation 2, we get this new equation number 4, which is -4y plus z equals 7. Now it's important for you to realize that what we've done is we're going to change equation 2 into equation 4. We used equation 1, or a multiple of equation 1. We multiplied it by -1. We are not changing equation 1. We have now changed equation 2 into what you see now as equation 4. So notice 1 has 3 variables. Our new equation 2, which is number 4 here, only has 2 variables. We're going to do the same thing with equation 3, okay? So we're going to use equation 1, we're going to multiply it by -3 so that we can add it to 3 and get the x to disappear. So we multiply equation 1 by -3, we then add it to equation 3, and we get this new equation, -13y minus 4z. So we now have these 3 equations. Our original system, this is the same system, we've just simplified some of these equations. But now we want to get rid of the z in the last equation, okay? If we multiply equation 4, which is our second up here, by 4 to make the z coefficient a multiple of the z coefficient in the equation below it. If we multiply this number 4 equation by 4, notice now we'll have positive 4z and negative 4z to get rid of z in one of these equations, okay? Here we've multiplied equation 4 by 4, and we've gotten this new equation number 6. I know it's a little bit confusing because we keep getting new ones. If we add these 2 equations together, notice what happens. We can now solve for the variable y. Okay? Since we've solved for the variable, well, I'm sorry, we can use this as our last equation, okay? Because remember, we're trying to do the Gaussian. So 3 variables, 2 variables, and now we've got it down to 1 variable by getting rid of the z. Now, why didn't we get rid of the y? Well, look at the coefficients on y. We've got -14 and -4. You know, we'd had to multiply these together. We got really large numbers. Where the z has just a -4 and a 1, whenever you have a variable with just a 1 in front, that's an easy one to get rid of because we just multiply it by the number in front of the other. So now we have 3 equations in Gaussian form, 3 variables in the first, 2 variables in the second, and only 1 variable in the third. So we're going to solve these systems by working from the bottom up. If we solve equation 7 for y, we get y equals -1. We then plug this value, we go up an equation, we plug in the value y equals -1 into equation 5, and we get z equals 3. We then plug both the -1 for y and the 3 for z into equation 1 and solve for x, and we get x equals 6. So our solution to this original system of equations is 6, -1, 3. I wanted to show you this visually. The graphs of a linear equation in 3 variables is a plane. It's like a sheet of paper, if you will. Thus, the solution set of such a system is the intersection of 3 planes. And there's a lot of different possibilities here, more so than the linear. We could have possibly one solution that these are at such an angle that they actually intersect in exactly one point. We could also have no solution in that there's no intersection of all three at exactly the same time, okay? In this case, you can see that each plane intersects with another plane, but there's no places where all three come together. It's also possible to have it in this other case where they're all parallel to each other. It's also possible to have infinite number of solutions where the intersection is actually a line. And then, of course, we can have an infinitely many solutions because they're all the same plane. Let's look at a word problem now. A food service distributor conducted a study to predict fuel usage for new delivery routes for a particular truck. Use the chart below to find the rates of fuel in rush hour traffic, city traffic, and on the highway. Notice here in week 1, in rush hour traffic, he drove 2 hours, drove 9 hours in city traffic and 3 hours on the highway, and he used 15 gallons of gas. And you can see how this goes across, okay? I don't like that they used X, Y, and Z for the variables here. I would have used R, C, and H because this would have connected me to the problem, reminding me that R is rush hour, C is city, and H is highway, okay? This was given in the problem, and this is great because this makes it really easy to convert these to equations. 2x plus 9y plus 3z equals 15. 6x plus 18y plus 6z equals 34, etc. Okay? So we have 3 equations just using the variable times the number of hours in the, for each week, and then adding them up to see how much total fuel was used. And here X, Y, and Z represent the hours in rush hour, city traffic, and highway respectively. So here are our 3 equations. Now we need to solve them. So again, we want to eliminate one of the variables from 2 of the equations. And when I look at these, I would pick Z because notice that Z has coefficients that are all multiples of 3. So that makes it probably one of the easiest ones to get rid of. Okay, so we're going to eliminate Z from equations 2 and 3. To do it from equation 2, we just need to multiply equation 1 by -1, because -3 and +3, add them together, and we have this new second equation, which we'll label equation 4. We're going to get rid of, notice we're going to try to do the same thing with equation 1 and equation 3. We multiply equation number 1 times -2, right? So that we now have a -6z here. But notice what happens when we do that. We got lucky that the y variable also disappeared. So we can actually solve this equation simply for x. We get 2x equals 4, so x equals 2. Well, this was like a little bonus because we didn't have to go through all of the steps to create the Gaussian. We already know what x is equal to, and we have the equation above with x and y, so we can use that equation to solve. Plugging x equals 2 into equation number 4, which we just created, we get y equals 1. And now we can plug in x equals 2, y equals 1 into the first equation and solve for z. And so we get z equals 2/3, or the solution to this system is 2, 1, 2/3. Now be careful because, often a problem asks you to tell what the answer is, but this doesn't really explain the answer contextually like the problem did. Remember that x was the number of the rate that we use gas in, is it rush hour? Yes. X was, see, this is why we use R, C, and H, because I don't remember what X is. Was X rush hour? Was X city? Was X highway, etc.? So using variables that are connected will really help us figure out the answer at the end. So in rush hour traffic, the distribution truck uses fuel at a rate of 2 gallons per hour. In city traffic, the same truck uses 1 gallon of fuel per hour, and in highway traffic, it only uses 2/3 gallon of fuel per hour. Okay, so that's a couple good examples. Hopefully this helps you. It just takes practice, and you just got to eliminate one of the variables. Again, like we did here, we're trying to look at, when we're trying to get rid of variables, look for coefficients that are hopefully more related, or maybe there's one with just a 1 in it. That's always helpful. Or multiples of the same number. For example, z was a multiple of 3. All right. Hopefully this will help you get through 6.2, and I'll see you in the next lecture.